All right, so checking out practice 7.5, 7.6, and the first one, just throwing a ball up, and in his first example, they're doing this on Earth, and then the question is, what if we did this on the moon? So what changes here is the acceleration due to gravity. When we throw the ball up, we're giving it kinetic energy. That's the initial energy it has. And then when it reaches its maximum height and it stops momentarily, that's its final energy. And so we get mgh. The initial kinetic energy has to equal the final potential energy at its maximum height. And the only thing we're changing here is g. So instead of 9.8 on Earth, it is 1.62 for the moon. And we're just being asked how high it goes, so we're solving for h. And the masses here will divide out, and we can just divide by g to get h. And somewhere it tells us the initial velocity here. And in the picture it does 20 meters per second. And that's what I'd punch in the calculator. At 123.5. That's question 1. So question 2, we got a 650 Newton woman climbing a staircase that makes that angle above the horizontal, and it's that long. Her speed is constant. Is the given weight a reasonable one for an adult woman? Well, the average mass for an adult is usually about 70 kilograms. So if we roughly multiply this by 9.8, which is 10, so mg here is about 700 newtons. So 650, sure, that's reasonable. Not the best question, but there you go. Part B wants to know how much has the gravitational potential energy increased by her climbing the stairs. So we have someone climbing some stairs, which I'm just going to make as a ramp. And we have an angle, and it says she's going to climb the staircase above the horizontal, and the staircase is 4.4 meters long. So I had to be careful what they're giving there. So that's the hypotenuse of the triangle. So if we want to actually get the height, which is the opposite leg here, then the opposite leg is going to be given by sine. So opposite over hypotenuse. And just multiplying both sides by 4.4 will give us what that height is. And she has a speed of 40 centimeters per second. So they want to know how much has the gravitational potential energy increased by her climbing the stairs. Well, we went from a height 0, the potential energy is 0 at ground level, and then we went 3.22 high. Potential energy from gravity is mgh, and mg, that's the weight they're giving us. They said that's 650 for m times g. And then our height here is 3.22. To get us 2091.7. For part C, how much work has gravity done on her as she climbs? Well, Gravity is a force that's going down, and climbing the stairs means you're working against that. And work is this force times your displacement cosine of the angle between. And when we connect these tail to tail, so vectors are always connected tail to tail here, then you're going up, going down. The angle between this is 180 degrees. And cosine 180 is negative. So the work we get here is actually going to be minus. And the work done by gravity is mgh. So we end up getting a minus mgh from the work done by gravity. And just looking at part B, looks like they rounded to 2100. So I'm just going to make that a minus 2100. So the work done by gravity was opposite the work you're doing. You're doing positive work to get yourself up the stairs. Gravity's trying to take that energy away. And taking energy away is negative. And those are the three parts. So this next one, we got a 72 kilogram person. So again, that's about average adult mass. Jumps into a swimming pool that's 4 meters above the water. All right. So maybe we got our swimming pool here. Here's our tree. 4 meters above the water. Use energy conservation to find the speed just as he hits the water. Well, initial energy is all gravitational. You're above the ground. mgh, h here being 4. And then when you hit the water, we'll call this where the zero potential is. So when you hit the water, all your gravitational potential energy is gone, converted to kinetic. So our final being 1/2 mv squared. And conservation of energy says initial has to equal final. So the initial potential of the gravitational potential has to equal kinetic energy when you hit the water. Mass cancels here, and we're looking for velocity. So just multiply both sides by 2, take the square root, and we have our velocity. To get 8.9. So if you're wondering, I'm just rounding to 1 or 2 decimal places here. And they did 1 to 2, but again, it accepted it, just so even though I said 8.9. Part B, use energy conservation again. To find his speed just as he hits the water if he bravely jumps straight up at 2.65. All right, so got a little different scenario here. So now we got our 4 meters, but you're going to jump up with some speed, 2.65. So that means our initial energy has some kinetic in it, because we're not just falling off that 4 meter cliff. We're not going to jump up. So we're giving ourselves some kinetic energy. And we have the potential energy still of being 4 meters above the surface here, where we have potential energy 0. So our initial energy is gravitational because we're above the ground level, and we're jumping this time, so that's giving us a kinetic. And then we go, we fall, and we hit the water, and when we hit the water, our energy final is just going to be all kinetic, since we're now at ground level here. And conservation of energy says these have to equal. So we have the initial velocity plus mgh of being above the ground, and that equals your kinetic when you hit the water. All these masses will cancel. And we do know the initial velocity, that's given. We know the height, that's also given. And so we can solve this for final velocity. And the first thing I would do here myself is I would just multiply everything by 2. And you might recognize this equation or not, but this is actually one of the kinematic equations from the beginning of the semester. And just plugging the numbers in then. So the initial velocity is the 2.65. The height here is 4. Do have to take the square root of all that as well to get a final velocity. And in part C, use energy conservation again to find his speed just as he hits the water. If he manages to jump downward. So same deal. Energy is not a vector, so it's not concerned about direction. In part B, we're jumping up. In part C here, we're now jumping down, but it's still going to be exactly the same result because our initial energy is going to be 1/2 mv squared from jumping down. We're still a height of 4 meters above the ground, and it's still going to equal our final energy that's just going to be kinetic when we land. So these two equations, same equations, they're going to be the same equations because, again, energy is not a vector, doesn't care about direction, doesn't care that we're jumping up here and jumping down here. Energy is just a number. And so the only difference is we're going to have our initial velocity here as 2.65. So 2.65 for jumping down. And again, I'd multiply, the masses cancel. I'd multiply everything by 2. We get this same equation here again, this one here. So I'm just going to use this again, except the initial velocity is now 2.65. And we get 9.2 as that final. So just to say that one more time, B and C are actually the same equations because energy is not a vector. It doesn't care about direction. It doesn't care whether you've jumped up or you've jumped down. You're still giving yourself a kinetic energy, which is this first term here. Whether you jump up or down, you're giving yourself a kinetic energy. And in each case, we're also the same height above the water. We get the same MGH. So checking out the next one. We got a force, 800 newtons, stretching a spring. All right, so spring has potential energy of 1/2 kx squared. They want to know the force constant, and in this case, we will have to get the force constant from the spring result. So Hooke's law, F equals kx. K is the spring constant. There's technically a minus sign in here, minus kx, but we're just looking for the k value here, so we're not going to worry about the minus sign. Our force being applied is 800. And the distance stretched is 0.25. We're just looking for the k value from that information, 800 divided by 0.25. So the minus sign, this is F equals minus kx is the actual force for the spring. But again, we're not worried about the direction. The minus sign gives us the direction of the force. This information here, we're only worried about what the k value is. And so we got our k value. K value is always positive. There's our k value for the spring. That represents how stiff the spring is. And that's part A. They want to know what the spring constant is. For part B, how much elastic potential energy is stored in a spring when it's stretched? All right, so now that we know the spring constant, we can use the potential energy for a spring. And we have K, 3200, And now we're stretching it 0.3, stretching it 0.3. So that's 1/2 kx squared. This is the potential energy of a spring. This is the force of a spring. And I'm just going to punch this one into my calculator. And for part C, how much potential energy is stored in a spring was compressed by 0.3. Did we just do that? Oh, okay. Part B is when it's stretched, and part C is when it's compressed. So these are the same values. So in the equation for potential energy, 1/2 kx squared, this x is the distance from equilibrium. So when a spring is just hanging out by itself, it has some equilibrium distance, your spring, and whether you stretch it a distance x or compress it a distance x, the result is always 1/2 kx squared, whether you stretch or compress. So part C is the same answer as part B, stretching and compressing. Both are 1/2 kx squared. And for part D, how much work was done in stretching at 0.25? All right, so let's just look at the energy real fast for that. So 1/2 our spring constant, 3,200, and 0.25 is what we are stretching it. I'm just going to figure out what that number is quick. All right, now they're asking for the work done. So we do have to be a little bit more careful here because they're not just asking for the potential energy. Because that's what I figured out here. I just straight up figured out the potential energy. They want to know the work. The work will mean if there's a plus or minus sign here. So we are stretching the spring. So imagine our spring. Here's our equilibrium position. We're going to stretch it, which means our distance is going to the right. But the force on a spring is pulling to the left. So we're stretching it. So we're pulling it to the right. And the force is working against us. It's pulling back against us. And so connecting these vectors tail to tail, this is a 180-degree difference. And work is force times distance with this cosine angle. The cosine angle is the real important part, because 180 degrees, cosine 180 is minus. And so we're actually going to get minus this energy here. So the spring, any of y'all felt that? Did I get 0.25? Well, they're not going to accept the minus sign here. Well, I'm going to have to get really nitpicky here. It's asking how much work was done in stretching. So there is two things happening here. Either you are stretching the spring, you're pulling it apart. That means you are doing work. So if you're, let me try to get another piece of paper here. If you're stretching the spring to the right, that means the force you apply is also to the right. So this is you. If you're pulling on a spring, you're pulling it in the direction of displacement. In this case, connecting these vectors tail to tail, their angle is 0, and then cosine 0 gets us 1, and so our number would be positive for that. So the work you do on a spring is positive, but the work the spring does is negative because the spring is trying to work against how you're pulling here. So I initially read part D as being the work the spring is doing, but since they're not accepting the minus sign, they're actually asking how much work you are doing. So it would have been nice if they had the word maybe you in here. How much work are you doing on a spring? Because then that would be positive. But the work being done by the spring is actually negative here. So we'll check out, just to say that again, the spring is pulling against. So when you try to stretch the spring out, the spring is pulling against you. The spring does negative work. It's trying to fight against you. It's trying to take away your energy. So this would be a minus sign for the spring. But if you pull the spring, your force is in the same direction as the displacement. And again, that's 0 angle, and that comes out to be a positive work then. That's the difference in the minus sign with part D. You do positive work on a spring, but the spring is doing negative work as it tries to fight against you. Now check out next one. Another spring storing that energy when it's stretched. So looking at this information, say whenever you're dealing with a spring, you're almost certainly going to want to know the spring constant, the K value here. And a lot of times the problems will just tell you the K value, or they'll give you information like this to help you determine the K value. So in this case, they're giving us this information. They're telling us that the potential energy is 11.1 that's being stored in a spring, and they're telling us it's being stretched 2.9 centimeters. And we're going to put that into meters, so 0.029 squared. And then this will allow us to solve for K, the spring constant. And that's what I'm going to plug into my calculator to determine K. And that is a pretty large value. So part A, how much potential energy would a spring store if it were stretched an additional, right, so they're being a little tricky here, an additional 2.9. So it's already stretched 2.9 centimeters, and we're going to stretch it another 2.9 centimeters to get us 5.8 centimeters for a total stretch. We need to put this into meters. So 0.058 meters is the total stretch of the spring. We know the spring constant, just figured it out here. Whoops, I got sloppy there. I meant to write 1/2 kx squared, and then I was going to plug this stuff in. So 1/2, we just figured out k. And we're stretching it a total of 0.058. And that gets squared. And then this, I'll punch into my calculator to figure out what that energy is of stretching it an additional 2.9 centimeters. So 44.4. And just to say this one more time, because maybe some people get stuck here, when you're dealing with the spring, you gotta know K. You gotta know what the spring constant is. And a problem will it will either directly tell you, it'll say, K is 1,000, or they'll give you information like they did for this problem, which helps us then determine K. So either way, when you're dealing with a spring, try to remember, okay, I'm going to need this number for K, and it's got to be given in some form. So looking at part B, how much potential energy would be stored if it were compressed by 2.9 centimeters from its equilibrium position. Okay, so we're doing exactly the same thing, except instead of being 0.058, now it's only being 0.029. So 0.029 is 2.9 centimeters. That is 1/2 kx squared. Oh, 11.1. That's actually our starting information. So I guess we didn't need to do that one again, because that was the starting information. 11.1 joules is actually our starting information. 11.1 joules stretched 2.9. So I suppose we could have just wrote that number in there, written it in. But moving on, how far from the equilibrium position would you have to stretch the spring to store 22? So we're still taking everything here is just using 1/2 kx squared. We already know what k is. They're asking us now to figure out what x should be so that the total energy stored is 22.2 joules. So we're solving for x. So divide by k, multiply by 2, and we'll have to take the square root there to figure out x. So 5.8. Ooh, we got to be a little careful here. Part C. Notice the unit here says centimeters. Little unfortunate because that might catch you. So my answer here is in meters. So 0.058 meters is 5.8 centimeters. So be a little careful if they're going to change the units on you because that's some way to get a little tricky. Oh, they don't like that. All right, so just looking at my calculator, I ended up typing a 4 in my calculator here. I ended up typing a 4 for some reason when I should have a 2. Now that I put a 2 here, I get a different number. So 4.1. So just to say that again, that was just a calculator error here. Instead of putting a 2 right here, I put a 4 for whatever reason. But now that I put a 2 in my calculator, getting the 4.1 centimeters. And for part D, what is the force constant of this spring? Well, that's funny. That's funny to me because we couldn't do the first 3 parts without K. So notice K was the very first thing I solved for here. And again, let me just state this again. When you're going to be dealing with a spring, the spring's energy is 1/2 kx squared. And almost certainly, we're going to need to know K right off the bat when we're dealing with a spring. So that was the very first thing I did in part A. So kind of funny they ask it at the very end. Maybe at the very starting that would have been better. But either way, there is number 5. So what's we got here? We got hailstones originate 520 meters above the ground and neglect resistance as we always do. How fast is it going when it hits the ground? So, does it quite say? So it doesn't quite say, but you know, we're assuming that our hailstone just forms from rest. Doesn't quite say that, but that's our assumption here. And it's some height above the ground. And that is important because if it's starting at rest, then it has no kinetic energy. So if it's starting at rest, the only initial energy it has is from gravity, mg8. So it's some height above the ground. It has potential energy from gravity. And we are going to assume it starts from rest. How would you know that, you know, looking at the problem? Well, they don't give us an initial velocity. So that is kind of implying that it's starting from rest because we couldn't solve the problem if they didn't give us an initial velocity. So you can always ask me what the assumptions are. I have no problem letting you know because you should know. And I think that's part of the trouble. The challenges with physics is you may not know the assumptions being made for certain problems. And when it falls, right as it hits the ground, it has no more potential energy from gravity. It's all kinetic now. And so we get this very common relationship we've been seeing. Energy initial equals final, where we get mgh equals 1/2 mv squared. The masses cancel. And if we're looking for velocity, we'll just multiply both sides by 2, take the square root, and we get our velocity there. This is actually 101 if I round. 101. And part B, express your answer in miles per hour. So there we go. I'm just going to pull up a web browser because I don't feel like doing that conversion. And I don't have a problem with you doing this either. 100 meters per second, 226 miles per hour. And again, for our tests and stuff, we're well past doing unit conversions. That was the first couple of weeks. Now we're at the end of the semester. Unit conversions is just busy work is how I see it there. So I don't have any problems with you just doing that and looking it up. And again, I'm not going to do that to you on a test. So we'll check out the next one. We got Io, a moon of Jupiter. It's volcanic. All right. It sends plumes 500 kilometers high. Gives us an acceleration due to gravity. And it's asking, what must be the speed of the material just before it leaves the volcano to reach 440 kilometers? So we have our volcano, and it's going to eject this piece of matter. And this matter is going to go a height of 440 kilometers. Now, the nice thing about the metric system is the K is the prefixes, literally just mean a number. K means 1,000. So if I want to convert this to meters, I'll just throw on another 3 zeros there for 1,000. So 440,000 meters is our height. The initial energy is it's given some kinetic energy upon its explosion, and then it rises up from that explosion, and it reaches some maximum height. And that maximum height is where it stops momentarily before it falls. And at maximum height, there will just be mgh. And again, we get this very common relationship. Initial equals final. 1/2 mv squared equals mgh. These m's cancel. We have to be a little careful here with g because it's on a different planet. And what do they say g is? 1.81. And so we're looking for the initial velocity this piece of matter must have had to get to that maximum height. And so 1,262 meters per second, that is really fast. So about 25 meters per second is about the speed limit on the freeway, about 65 miles per hour, about 25 meters per second. So this is way, way faster, 100 times faster almost than driving your car. Thinking about part B, the gravitational potential energy is 0 at the surface. What's the potential energy of that fragment at its maximum height? Okay, so all they're asking for is mgh. They're just looking for potential energy, because that's what it says. Well, it says it's 0, so they're saying potential energy is 0 at ground level. So again, very common to do, put potential energy 0 at ground level. It's at some height, and they're asking what's the potential energy from gravity at some height. The mass is 23 kilograms, so the mass is 23. G for this again was 1.81. And then they do give us a new height this time of 500 kilometers. So 500, K means 1,000, so I'll put in another 3 zeros there. and I'm just going to type that number in. So again, this is what I just do here. I just did MGH is what I just did. So I am just going to shorthand that. So that is 2 times 10 to the 7th. So that I'm just going to write this. That's 2 and 1, 2, 3, 4, 5, 6, 7. And then for part C, how much would this gravitational energy be if it were at the same height above Earth? All right. So the only thing that changes here about Earth is the acceleration due to gravity. So Earth is a lot bigger than the moon Io, so it's got a higher acceleration due to gravity from its mass. So I'm just going to calculate the same number again, but have 9.8 instead of 1.81. And that'll give 1 times 10 to the 8th. So that'll be 1 and then 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And it's probably going to want me to round a little bit. And I'll just see what the rounded answer is. It's 1.1. So I guess I should have rounded. That's fair enough. I mean, my calculator does say 1.127 times 10 to the 8th. So I've rounded a little bit too hard there, I guess you could say. I should have kept one more decimal place. And that is number 7. So we have a 28 kilogram child is playing on a swing, having supports that are that long. A friend pulls her back until the ropes are at that angle. What is the potential energy of the child just as she is released? So we might need a little picture here to help our brains along. So here's our swing, but she's being pulled back by a person at an angle of 45 degrees. So she's being pulled back. So she's right here. You know, a swing, how you swing around back and forth. So she's pulling back. Here's our ground level. Call that our potential energy 0. And the rope is 1.9 meters long, this rope. Now, another assumption that's going to be made here, and I know it's going to have to be made because they don't have enough information, is that right at the bottom, we're touching the ground. So in the real world, the swing doesn't actually touch the ground of the swing. There is some height of the swing above the ground, but we're going to ignore that because they don't tell us what that height is. And if we don't ignore that part, then there's no way for us to actually solve the problem. So again, another assumption that may be tough to know as a learning physics, but we are assuming that this swing will actually swing right against the dirt. So in other words, your butt will scrape against the dirt. You'd have to hold your legs up into the air, but that's the assumption being made here. So we're looking for this height above the ground. So let me try to draw a bigger picture here. Here's our arc, and we're looking for this height right here. This is the height we're looking for, is that height right here. Now this is a circular trajectory, meaning this is a circle, because the height of the swing is some fixed length. And we want to know what this leftover distance is here. So we have a right triangle. We need to figure out then what is this leg, just this part from here to here. And we're given an angle of 45. We also know this is 1.9. So let me draw another picture. 1.9 is the hypotenuse. Here's our angle of 45 degrees. And we're trying to figure out what is this adjacent leg. And the adjacent leg is given by cosine. So cosine is adjacent, which we're trying to find, over the hypotenuse. And so we can define the adjacent leg by just doing 1.9 times cosine 45. So I guess I'm using a question mark here for adjacent. It's 1.34. So let me just try to draw the picture again and try to make this as clear as possible. So we have our circular trajectory from our swing. We're swinging back and forth on this circular trajectory, again, because the rope that suspends us doesn't change length, so we follow a circular pattern here. We know the total length from top to bottom is 1.9 because that's the length of the string. And then we just figured out this distance right here is 1.34. And so the distance that's left over this distance left over here then is 0.56. That's how high the child is above the ground. So here's our ground. Remember the swing is going to scrape against the ground here. So when a child is pulled back to this point, they're 0.56 meters above the ground. So looking at the potential energy, which is mgh, we have the child's mass, gravity is 9.8, and the tough part there was figuring out what height we have. That's 0.56. Oh, the child's 28 kilograms, 9.8 for acceleration due to gravity, and we figured that height the child is 0.56. So the potential energy, that one took a little bit longer to get to. Oh, and they gave us a picture here. So, well, they had the child swinging from the left. I had my child swinging from the right. Doesn't matter. Doesn't matter at all. Part B, how fast will she be moving at the bottom of the swing? Okay, so she's starting, I keep saying she. Is it a she? Yeah, they do say she this time. How fast will she be moving? So she's starting right here. Here's where she's starting, right here. 0.56 above the ground. She's going to swing, and her butt's going to scrape against the ground because that's our assumption here. And so all her potential energy will convert to kinetic. So our initial potential energy is going to equal the final, all kinetic, right as she gets to the bottom of the swing there. Masses do cancel. They're asking for velocity. So again, we get this very familiar relationship in solving for v squared of 2gh, where h is the 0.56 we figured out from earlier. And so her velocity when she gets to the bottom of that arc, 3.3. And in part C says, how much work does the tension in the rope do as the child swings? Okay, well, that's being a little tricky. So if you can remember back to work is this force times distance, cosine of the angle between them. So going back to my picture, the child is moving in this circular pattern here. That's the trajectory of the child. They're moving in a circle. The tension is along the rope. So the tension is going up like this. But her pathway is always going like this. It's always 90 degrees. So the path the child takes is always 90 degrees with the tension force. And when we look at the definition for work, When the angle is 90, cosine 90 is 0. So the rope is not doing any work here because you're not moving against the rope. And again, the reason for that is the rope. So here's my child, is dot. The rope is pulling the child that way, but the child is always moving 90 degrees to the tension of the rope. And that 90 degrees, cosine 90 is what gets us a 0 there then. Looking at the next one. So we got a spring with that constant is anchored to the wall on one side of a hockey rink, all right? A hockey puck is pressed against the spring and then released to slide across the ice. If the process, the hockey puck gains a kinetic energy, drive an expression for the initial compression of the spring in terms of the spring constant and K being kinetic energy here. So you have your spring and it's compressed with this hockey puck. That means the initial energy is all from the energy being stored in the spring, which is 1/2 kx squared. And then the puck gets released from the spring, and now it's off doing its thing with some velocity. In this final picture, now it just has energy of motion, which is kinetic energy. And so energy initial equals final. All the energy of the spring, 1/2 kx squared, all that energy is going to go into the motion of the puck. And they ultimately want us to solve for, well, just looking at the answers here, all these have a minus sign except for the last one. So the last one's the one that's correct. But just to look at this here, the 1/2 will divide out. And we're solving for x. Oh, let me unclick this because I see they say compression. We'll have to say something here in a minute. But we are trying to solve for x. So we'll divide by k. And we do have to take the square root here. So whenever you take the square root, you do get a plus or minus solution. And that works out for the spring, because if I have my equilibrium position here, that's my equilibrium position. This is considered to be where your 0 point is, the 0 of our coordinate system. So when we stretch to the right, that's considered a positive stretching. If we compress it, that's considered to be a negative x. Again, the equilibrium position of the spring is considered the origin, where the number 0 is. So to the right is positive. To the left, is going to be negative. So compressing the spring will force us to take the negative of the square root. Because we are compressing it. It does say here the initial compression of the spring. And see what we get. And I noticed they wanted this in terms of kinetic energy, which is not what I did here. I just solved it straight up. They want this in terms of kinetic energy, so let me just rewrite this fast. Our initial energy is the spring. They want this in terms of kinetic energy, which means they don't want us to write the 1/2 mv squared there. They just want to say kinetic energy. So if I solve this, divide by k, multiply by 2, take the square root, take the minus root since we're compressing. And this is actually what you're looking for. I use KE for kinetic energy. That's pretty common. They're just using K, so we have 2 capital K over little k, which is a little unfortunate. But so we have, that would be then the first selection. So we have 2 capital K divided by lowercase k. taking a square root. Here's our minus sign, signaling that we are compressing the spring. All right, let's take a look at the last one. We got a 17 Newton package of flour is suddenly placed in the pan of a scale. The pan is supported from below by a vertical spring of force constant. So notice they give us the spring constant. So we're going to need that. 315 is our spring constant. If the pan has negligible weight, so we're going to ignore the weight of the pan of this, find the maximum distance the spring will be compressed. And again, we're ignoring any energy loss from friction, as we always do. So we have the weight of the spring, or I mean the weight of the package. So if we look at our package here, our package has some weight, mg, which they're telling us is 17 newtons. And then what's supporting the package is the force from the spring, which is kx, the force from a spring. And so Newton's law says we got kx going down, mg. It's not moving. It's not moving, so I'm doing a summing of forces here, which we haven't done for a while, but looking at sum of forces, the force from the spring has to support the weight. They're in equilibrium, so Newton's second law says this equals ma, but a is 0, and so we get kx equals mg, and what are we trying to solve for? We're trying to solve for x, how much it's compressed, so that's just going to be mg over k. And again, mg they're telling us is 17, and then k they said is 315. And that is another thing to be careful about. Just looking at Mastering Physics, they do have the units here as centimeters, so not standard units. So my answer is in meters. To get this into centimeters, you've got to move the decimal place to the right twice. So 5.4 centimeters there. And, well, they didn't like that. All right, so this was my mistake on this one. Perhaps a minor challenge. Being a physics person that sees these problems constantly is you kind of make a quick assumption on how the problem's going to go. So let me say this. I assumed that it was in equilibrium, and I wrote that right here actually, that the forces were balancing each other, but they're taking the position and that when you put something on a spring, that the spring, if you just drop your object, the spring will compress and then kind of push up and compress and push up until it reaches the point where it's at an equilibrium, just holding the spring. And that's what I solved for. I solved this point when it's all in equilibrium, the forces are now all balanced, the spring is just supporting it there. But they actually are talking about this first part. If I just drop my object, it's going to compress the spring. It's going to oscillate until it finally finds its equilibrium position. In other words, they're taking the position that this still equals ma, that there is an acceleration. And we can then deal with energy on this. So the spring, it's a maximum compression. If we call that potential, let me show that picture. If we show the maximum compression, if we choose that as being potential energy 0, which is what we're going to have to do to solve this problem, then the spring will compress all the way down here, but then it'll oscillate a little bit until it finds its equilibrium position, which will be a little bit above that lowest point. And if we look at that, the initial energy here is going to be mgx, the compression of the spring. And then when the spring gets fully compressed, it'll have its energy of 1/2 kx squared. And then they set these two equal because energy is conserved, that the initial potential energy has to equal the potential energy of the spring. Our x's will cancel here, and just looking at this, we get 2mg over k. That's what our x is. Notice for x I had mg over k. This is 2mg over k. And again, to state the difference here is I assumed that that was an equilibrium, so that the spring had found its equilibrium position, but they're taking the position, I mean, they're writing the problem so that we're dropping it. The spring oscillates until it finds its equilibrium position. They're looking for that maximum compression that's right here when you drop it. And then we can get that by using energy, choosing potential energy to be 0 at maximum compression of the spring. And then our height for potential will be x, the actual compression of the spring. And then we can solve for x. And so my answer was 5.4. They have 10.8 because that is going to be twice the value, which comes from that 2 right here. So that was my mistake. I did assume it was in equilibrium when they didn't want that. And if you actually read to the bottom here, they do say the system is not in equilibrium. And though that was my error to assume that. And there is number 10. So check out for the next practice homework coming up.